Alright, so today we're going to have a look at the topic 4, more concepts about functions. And in this lesson, we'll talk about the meaning of monotonicity of a function, parity of a function, transformation of a function, the basic arithmetic operations to functions, which means addition, subtraction, multiplication, and division. And then finally, we'll talk about function composition. So since now we have learned two types of very simple functions, linear and quadratic, right? So in this lesson, we'll use these two functions. We mainly use these two functions as examples. Occasionally, we'll touch some other types of functions, but do not go that deep. So we'll use these ones as examples. Okay, first, the meaning of monotonicity of a function, which means whether this function is increasing or decreasing in some interval. Monotonicity describes the increasing or sometimes strictly increasing or decreasing or strictly decreasing behavior of a function on an interval. And strictly speaking, a function fx increases on an interval I if we have fb is greater than or equal to fa for all b is larger than a, where a and b belongs to the interval I. And if for any b is greater than a, you always have fb is greater than fa, then the function is said to be strictly increasing, which corresponds to, well, increasing function corresponds to the first diagram here. Strictly increasing function on an interval from Mn corresponds to the second graph. You can have a look at. This will give you an intuitive way of looking at the functions, increasing functions on some intervals. And conversely, a function fx decreases on an interval I if for all b is greater than a in that interval, you always have fb is less than or equal to fa, which corresponds to the scenario here. Or for any b is greater than a in the same interval, you always have fb is less than fa, which corresponds to this diagram. Then we say this function is strictly decreasing in this interval. For example, in this diagram, that interval is from m to n, inclusive both sides. And if this function does not satisfy either, then on some intervals, then they say it's not monotonic on the interval I. For example, the last diagram shows fx is not monotonic on the interval from m to n, because sometimes it's decreasing, sometimes it's increasing. It's not monotonic. Are you clear? So these are just some mathematical terms. Make sure you know the terms, the meaning of the terms, and make sure we are speaking the same language. Okay?
Okay. Yeah. Can I just write this down real quick?
Yeah. So these are the rigorous definition of increasing or decreasing function on some interval.
Okay.
So if a question asks you to check or prove if a function is increasing or decreasing, so far we haven't learned any other methods. You can just use the definition to prove whether this function is decreasing or increasing in some interval I. Okay?
Okay, wait 1 second, I'm not done yet.
Okay.
Okay, I'm done.
Okay, make sure you understand the definition. Okay, preferably memorize them based on the understanding. So let's have a look at examples. So usually when we introduce a new concept, I'll give you an example first, okay, to illustrate the abstract concept. So here, question asks us to prove that the function y equals 2x squared plus 4x minus 3 is strictly increasing on the interval from -1 to positive infinity. So first, let's have a look at the graph of this function. Again, we have already studied. The function is actually a quadratic function. We know its graph, right? It's opening up, and apparently there are 2 zeros, but for monotonicity, we only care about its axis of symmetry, right? So intuitively speaking, on the right side of the axis of symmetry, this function is increasing. And on the left side of the quadratic function, the function is decreasing. As x increases, y decreases. To the right of the axis of symmetry, as x increases, y also increases. So it's increasing function. So that's intuitive looking at this function. Looking at this function intuitively, right? So can you actually prove? So we know this axis of symmetry is x equals -1, because we know that x equals negative b over 2a, right? You see that? The axis of symmetry of this function is x equals -1. So can you prove that when x is greater than or equal to -1, this function is actually increasing? And like I said, we haven't learned any other methods so far. Once you learn the calculus, basically you can use the derivative to check if a function is increasing or decreasing. But so far, we haven't learned that yet. So the only way we can use here is to use the definition, right? So usually we can do this. We choose. So basically, you need to prove that for any x less than x2, we also have fx1 is less than fx2 on some interval, right? Then this function is strictly increasing on that interval, right? You follow me? So for this purpose, we can choose any x1 and x2. So we say we can choose any x1 and x2 such that st means such that, okay, -1 is is less than or equal to x1, which means x1 is greater than or equal to -1, and x2 is greater than x1. So we need to prove. Note that we need to prove for any x1 less than x2, we always have fx1 is less than fx2. Then this function is strictly increasing, right? So this is your target. So can we prove that? So in order to prove that, first we need to find what is fx1. So fx1 is simply to insert x1 into that equation of that function, which is 2x1 squared plus 4x1 minus 3, right? And we also need fx2. fx2 equals 2x squared 2x2 squared plus 4x2 then minus 3. So we need to check whether we have fx1 is less than fx2, which is equivalent to say you need to check whether fx1 minus fx2 is less than 0, right?
Yeah.
So of course fx1 minus fx2 is
not less than 0.
Yeah, it's 2x1 squared minus 2x2 squared, then plus 4 times x1 minus x2, right? The negative 3 just cancels with each other. So we can factorize the first one, which is 2x1 plus x2 times x1 minus x2, then plus 4 times x1 minus x2. We need to check the sign in front of fx1 minus fx2 to see whether it's a positive or negative number, right? So it's better to factorize that to a product of several terms, several factors. So that equals 2x1 plus x2, then plus 4 times x1 minus x2, right? Can you see the symbol now? Okay, you can't see that. You can analyze it a little bit. Note that we have x1 is greater than or equal to -1, right? And x2 here is greater than x1. So it's greater than -1, right? So we have x1 plus x2 must be greater than -2. And if we multiply both sides with 2, then we have 2 times x1 plus x2 is greater than -4, which is this part here, right? And then we can add 4 to both sides of the inequality. That does not change the equality the direction of the equality symbol. So 2x1 plus x2 plus 4 is greater than 0, right? Also, note that x1 minus x2, which is according to here, x1 minus x2 must be less than 0, right? Which basically means this part is less than 0, and the first factor here is greater than 0, right? So the product of these two numbers must be less than 0. Therefore, we have fx1 minus fx2 must be less than 0, right?
Yeah.
Okay, so that means for any x1 is less than x2 in this interval, we always have fx1 is less than fx2, which means smaller input always indicates smaller output. So this function is strictly increasing on this interval. So fx is strictly increasing.
Yeah, that makes sense.
On this interval. So this is how we can prove the monotonicity of a function on some interval I. Okay? Did you get it?
Yeah, I get it.
Okay, so can you try this by yourself? Do you have a pen or you just use mouse to write on the screen?
When I run the screen, it's using my mouse, so it's like.
Okay, so yeah, mouse is very difficult to write on the screen, right? I think you can just write on a sheet of paper.
Okay.
Just let me know if you finish, okay?
Okay. Okay, I think I'm done.
Okay, so you don't have any questions, right?
Yeah, no. I understand.
All right. Okay, so let's see the next one. So next concept is called the parity of a function. The parity of a function means whether this function is even, odd, or neither. Okay, again, let's have a look at the definition. A real function f is even for every x in its domain. Negative x is also in its domain, and f negative x equals fx. This means if for all x you always have f negative x equals fx, then this function is an even function. And geometrically, the graph of an even function is symmetric with respect to the y-axis. Can you see why? Because suppose we choose any arbitrary point on the curve of that function. So if you simply let the x coordinate be negative x, then negative x must be here, right? If f negative x equals fx, then these 2 points will be symmetric in the y-axis. So if every point is symmetric in the y-axis, then this function is symmetric with respect to the y-axis, right?
Yeah.
Okay, and similarly, a real function f is odd if for every x in its domain, negative x is also in its domain, and you always have f negative x equals negative fx. Which means if you can prove for any x on the curve of that function, you always have f negative x equals negative fx, then that function is called an odd function. And geometrically, the graph of an odd function has rotational symmetry with respect to the origin, meaning that its graph remains unchanged after rotation of 180 degrees about origin. For example, if you have a function whose graph like this, then you can actually prove f negative x equals negative fx. Then this function is odd, and we see that this odd function has point symmetry in the origin here, which means if you rotate this function about the origin for 180 degrees, the graph of this function will on top itself. This is called point symmetry in the origin. You get it? Or a much simpler function is a linear function. So suppose you have a linear function here which crosses the origin point. It's also a odd function, and it has point symmetry in the origin point, because if you just simply rotate this function about the origin for 180 degrees, the graph of this function will on top of itself, right?
Yeah.
Okay. Any questions? Okay, I'll show you an example. Okay. So can we prove the function here is an even function? Again, we haven't learned any other methods, so we can just use the definition here, which means we need to prove that for any x in the domain of fx, we always have f negative x equals fx, right?
Could you give me some examples for even and odd?
Yes. Okay. Let me finish this first. Okay. Okay. So we can say for any x in the domain of fx. So what is the domain of fx? It's actually the whole real number set. There's no limitation, right?
3 pages of notes already. Thank you. I always do a good job.
So for any x in the domain of fx are we know there's no limitation. X can be any real number R, right?
Yeah.
So for any X can be any real number in the set of R. So we need to prove f negative x equals fx. We have, so in this case, what is f negative x? F negative x is simply negative x squared plus 5, right? Which can be simplified to x squared plus 5. And we know x squared plus 5 is simply fx, right? So in other words, you have proved for any x in the domain, we always have f negative x equals fx. So according to the definition, this function is an even function, right?
Yeah.
Okay, so we can use a 2 to show its graph to see whether its graph is symmetrical about the y-axis. Okay, again, let's use GeoGebra. The function is y equals x squared plus 5. Y equals x squared plus 5. So that's its curve. See? It's symmetric in the y-axis, right?
Yes.
So I'll give you another example. Some other example. Although we haven't learned this type of function, but so far we'll just use it as an illustration of some other types of even functions. So how about this one? Is it even or odd? Or neither?
Even.
Yeah, because you can always prove that f negative x equals fx in its whole domain, right?
Yeah.
And again, let's check its graph. So this time we have y equals 1 over x squared. Okay, yeah. See, this is its graph. See, it's also symmetric in the y-axis, right? Did you get it?
Yeah. Yes.
Okay, I'll give you another one. How about y equals the absolute value of x? Is it even or odd?
Even.
Even, yes. Again, if you check its graph, y equals the absolute value of x. So this is y equals absolute value of x, right? Again, as you can see here, it's also symmetric in the y-axis, right?
Yeah.
Okay. All right, then let's do a practice here. Can you determine each of the following functions is even, odd, or neither? And let me know if you finish, okay? We have already done this. This is the third one is an even function. Okay, can you explain a little bit why the first one is neither? So what makes you think it's neither odd or even? So currently we can't use some other methods. The only method you can use is its definition, right?
Yeah.
If you recall the definition of odd function, if you can find any x in its domain, such that f negative x is always negative fx, then that's an odd function. Or if you can find any x in its domain, you always have f negative x equals fx, then that's an even function, right?
Yeah.
Be careful with the definition here. So what about the first one? So for any x in its domain, apparently its domain is R, right? R is its domain. So for, let's say, for any.
Oh, this is odd.
Yeah. So we use this notation to denote for any x. So this symbol here means any.
Yeah, that's why it's odd. Because I messed up.
Okay, this symbol means for any x belongs to the real number set. Can you prove that f negative x equals fx or negative fx? Can you prove that? F negative x equals negative x to the third, right?
Yeah, because.
Does it give you negative x to the third? Yes or no?
Because if you times negative 3 times, it's still a negative.
Then you will get negative x to the power of 3, right?
Yeah.
So what is negative x to the third or to the power of 3? That's actually negative fx, right?
Yeah.
So that means for any x belongs to the real number set, we always have f negative x equals negative fx, right?
Yeah.
So according to the definition, is it odd or even or neither?
Odd.
Yeah, it's an odd function. And actually, if you check its graph here, okay, let's try to plot its graph. We have y equals x to the third. It actually looks like this. So as you can see here, it actually has point symmetry in the origin point, right? Which means if you rotate this function 100 degrees counterclockwise or clockwise, the graph of this function will on top of itself. That's called point symmetry in the origin point. Did you get it?
Yeah.
Okay, let me show that to you. So this is the graph of that function. If you, okay.
Yeah, because it's the same.
Yeah, if you rotate it 100 degrees, then it will on top of itself, right?
Yeah.
Okay, so how about the second one?
The second one is even.
Why it's even? Can you explain a little bit?
Because it's a parabola with a function going like that. No.
So the method you use to determine whether it's even or odd has to be the definition. Now, we haven't learned any other methods, right? So can you prove for any x belongs to the domain, can you prove f negative x is fx or negative fx or neither of the two?
If you use negative x, then it would become still basically x squared plus 6x plus 5.
If you insert negative x instead of x there, you will end up like negative x to the second minus 6 times negative x, not x, right?
Yeah.
You see that? So that'll give you x squared plus 6x then plus 5, right? Are they the same?
No,
or is this opposite? Or is the only difference is the negative sign? Or are they the same or neither?
Neither.
Neither. So you cannot prove f negative x is fx or negative fx. So this function is neither odd or even. Again, let's check its curve. So we have y equals x to the second minus 6x plus 5, right? So as you can see here, the curve is neither has line symmetry in the y-axis, nor the point symmetry in the in the origin point, right?
Yeah.
So it's neither even nor odd, because otherwise you will have line symmetry in the y-axis if it's even, or point symmetry in the origin point if it's odd. Now did you get it? So the key to determine whether this function is odd, even, or neither is to use this definition here to see if you can prove f negative x is fx, negative x, or neither, right?
Yeah.
Okay, and we have already covered the third one. And this is even because we can prove for any x in the domain f negative x is always fx. So according to the definition, that's an even function. So how about the last one?
It's neither, because when you put the negative x,
when you plug negative x there, what do you have here?
Negative 5x.
Negative 5x. Is it negative px? Is it negative px?
Yeah.
So you have actually proved p negative x equals negative px. Can you see that?
Yeah.
So if for any x belonging to the domain, you always have p negative x equals negative px, then you will have a odd function, right?
Yeah.
Again, this is a very simple linear function. We have already studied linear function. Y equals 5x. Any linear function which crosses the origin point is a odd function, right? Okay, if you rotate it in the origin point for 180 degrees, it will on top of itself, right?
Yeah.
It has point symmetry in the origin point. So I'll put a mark here. Careful with this type of question. Make sure you really understand the definition of even or odd function, okay? All right, next let's have a look at transformation of a function. So this means if you have a function like, for example, fx here, so after some transformations, you will end up with a new type of function, gx, and gx can be expressed in a way that has connection with fx. For example, if we simply move this function down here, then your new function gx can be expressed as fx minus a constant number d, right? Because the whole value of the function has been lowered by d units. Did you get it? We'll have a look at them one by one, okay? So have a look at them one by one first, and then in the last step, we'll combine all of the transformations. Okay, first let's have a look at vertical translation, and then followed by horizontal translation, then reflection in the y or x axis, then vertical stretch, horizontal stretch, and combinations of all the above transformations. Okay, first, vertical translation. First of all, translation means shift a function up or down without stretching or compression. So for example, if you have a function's curve here, if you move it up or down or left or right without changing its shape, that means transformation, okay? Translation, sorry. And the transformation theory states that the graph of the function gx equals fx plus c. So note that gx is the new function in which we add a constant number c to the original function fx. Then the graph of the new function gx is a vertical translation of the graph of fx by c units. If c is positive, the graph moves up c units. And if c is negative, the graph moves down c units. Okay, let me know if you finish, and I can show you an example. Okay.
Okay.
Can you see why this is true? Can you explain this a little bit? If I simply add a constant number after the original function x, why the new function is just vertically translated up or down?
Because b is like the y-intercept.
Yeah, because if you don't change the input x, then the value of the new function is simply increased by c unit or decreased by c unit, right? So that means if every point has a c unit shift up or down, the whole curve will be shift up or down. That's a vertical translation, right?
Yeah.
So here I can show you some examples. The original function is fx equals x squared. If we simply add a constant c after that, for example, let c be either 1 or -1, then you can see the relative position of the three curves here. The red one is y equals x squared. So if we simply add 1, then the whole curve will be shifted up. That's called vertical translation up by 1 unit. You see that?
Yeah.
And if you add a -1 after x squared, then the whole curve will be shifted down by 1 unit. That's called vertical translation down by 1 unit. Okay, so actually vertical translation is the simplest way of transforming a function. It's very easy to understand, right? Okay, let's see a practice let's see an example first. So how do we obtain the graph of the new function gx from the graph of a function fx?
You move the function up 5.
Yeah, so the only difference is 5, right? And usually we write it like this. We say note that gx can be expressed as, you need to establish connection between the original function and the new function, right? Gx can be expressed as fx plus 5. Therefore, we say the graph of gx can be obtained by vertically translating the graph of fx up by 5 units. You get it? You should write it like this. Are you clear? Okay, let's practice. So how do you obtain the graph of gx here from the graph of the function fx equals 3x squared plus 2x plus 9? Well, you should say, because gx equals fx minus 3, right?
Yeah. So you just move it up 3 units.
Yeah, what do you say here? The graph of gx can be obtained. Still, we repeat this sentence here. The graph of gx can be obtained by vertically translating the graph of fx. This time we need to translate down, right?
Yeah.
By 3 units. Did you get it? Well, this is like some standard statement you need to make to avoid any confusion, okay? Are you clear?
Yeah.
Okay, next let's have a look at the second translation, which is called horizontal translation. We have covered the first one. I'll make a mark here. The second one is horizontal translation. So can you make it a reasonable guess if I have original function fx, and then if I translate it horizontally by d units, let's say d units, and d is greater than 0, can you tell me what is the expression of the new function gx? Can you establish the connection between gx and fx? Well, what I mean is here, let me draw your diagram. Suppose this is fx, and gx is here. No, gx is here, which is simply translate fx horizontally by d units. How do you write the expression of gx? So in the first translation, if we do a vertical translation, then we have gx equals fx plus some constant c,
minus
right?
something?
Pardon?
Minus?
Yes, it should be g. Where do you write the constant? Here, right?
Yeah.
So x minus d. Can you see why? Can you explain a little bit?
Because d is like going left and right, so if you increase or decrease d, then it'll be moving left to right.
Yes, because if you want any y unchanged, you need to increase x by d units, right? So originally, if a point x0, y0 is on the curve of gx, is on the curve of fx, in order for y0 unchanged, now your new x should be x0 plus d, right?
Yeah.
Which means this point is on the curve of gx, and this point is the original point translated to the right by d units. So that's why it's a horizontal translation. Okay, very good. I think you understand it. And I'll give some example here. Again, let's use x squared as well. So x squared is here, right? The red curve. So if you add a 1 here, this is equivalent to x minus minus 1, right? Remember, x minus something is move to the right by some unit. So x minus minus 1 means move to the right by -1 unit, which is equivalent to actually move to the left or translate to the right to the left by 1 unit. Can you see that?
Yeah.
Which corresponds to the blue curve. The blue curve here is x plus 1 squared. And the green curve here is x minus 1 squared. Are you clear?
Yeah.
Okay. So let's have a look at an example here. How do you obtain the graph of gx equals x minus 2 squared from the graph of function fx equals x squared? Again, in order to answer this question, we need to establish the connection between gx and fx, right? Gx can be expressed as f of x minus 2, right?
Yeah.
So if we
So
add minus 2 here,
by 2 units.
yes, how do you write that? So we should say the graph of gx can be obtained by horizontally translating the graph of fx to the right by 2 units, right?
Yeah.
By horizontally translating. Okay, be careful with the word translating. The graph of fx to the right by 2 units. So you have to specify the direction and by how long. How far, sorry. Are you clear?
Yeah.
Okay, so can you try to write the sentence, the statement by yourself here? The original function is fx equals x squared. The new function is gx equals x plus 5 squared. Can you state how do you obtain the graph of the new function based on the original function?
So gx equals x plus 5 squared, which means it's moving to the left because d is increasing by 5.
Yeah, because gx can be expressed as f of x plus 5, right?
Yes.
Which is actually fx minus 5, which means in order for every y unchanged, your x must be shifted to the left. X must be 5 units lower than before in order to keep the y unchanged, which means to translate the curve to the left by 5 units, right?
Yeah.
So again, repeat this statement. This is a standard statement. The graph of gx can be obtained by horizontally translating the graph of fx to the left.
Right, left by 5 units.
Yes. Yes, just fill in the blanks. To the left by 5 units. Sorry, plural form, units. Units. Okay, I think you are already clear with that. Let's say actually the horizontal translation and vertical translation can be combined together. So let's say an example here. So suppose the original function is fx equals x squared, again, and new function is gx equals x plus 5 squared plus 1. So in this case, we can express gx as, first of all, fx plus 5, right? And it's not enough because fx plus 5 is simply x plus 5 squared. We have another 1 here, right?
So it's moving to the left 5 units and up 1.
There are 2 parameters which corresponds to 2 types of translations, right?
Yeah.
So we should state that. Yeah, I think I'll just show you the statement you should write here. I wrote it in advance, so that'll save us some time. Okay. Okay. Alright, so note that gx equals f of x plus 5 plus 1, right? Therefore, we say the graph of fx, the graph of gx can be obtained. Oh, actually, we don't need this now. Therefore, the graph of gx can be obtained by horizontally translate the graph of fx to the left by 5 units, and then vertically translate the graph of fx up by 1 unit, right?
Yeah.
Also, note that you can do the 2 types of transformations at the same time, or you can do the vertical translation first, followed by the horizontal translation. Or you could also do the horizontal translation first, followed by the vertical translation. The order does not matter, right? For translations, the order does not matter. Order of vertical and horizontal translations does not matter. So can you state the domain and range of each function?
For fx equals x squared, x is equal to any real number.
Yes. For fx, the domain is a real number set. The range is
anything bigger than 0.
Equal to or greater than 0, right?
Yeah.
So for, how about gx? Domain does not change.
Domain is the same, but now it's 1 because you're adding 1.
Yes. So in general, the domain range of a function of the form gx equals f of x minus d plus c can be determined by adding the d value and c value to restrictions on the domain and range, respectively, of the base function, right?
Yeah.
Alright, so we have finished the second one, horizontal translation, which is also easy to understand. Then let's see, reflections. So can you make a reasonable guess? Again, according to what we have learned for the previous 2 translations, if I have a base function fx and I reflect it in the y-axis, can you write the expression of the new function? I'll draw a diagram for you. Okay, reflection. Also, let's talk about reflection in the x-axis first. So suppose this is a fx. And reflection in the x-axis means this is a new function, gx. Can you write the expression of gx?
Times -1.
Yes. So we, where should you put the negative sign here in gx?
Before, after, like -g.
Here, right? Gx is simply negative fx. You see that?
Yeah.
That's correct. Again, very easy to understand. How about if I have a function here and then I reflect it in the y-axis?
G bracket -x.
Yes. Gx, well, actually gx equals f of negative x, not g of negative x.
Sorry.
Yeah, because if you simply keep y unchanged, you need to make x be the negative number of the base function, of the input of the base function. So that's f negative x, right?
Yeah.
Okay, again, let's do a exercise. Okay, the graph of function gx equals negative x is a reflection of the graph of the function fx in the x-axis. Okay, let's see an example. How do you obtain the graph of gx equals negative x squared from the graph of the function fx equals x squared? How do you make the statement? So what's the relation between the two functions? Note that gx is actually negative fx, right?
Yeah.
So we say the graph of gx can be obtained by reflecting the graph of fx in the x-axis. You get it?
Yeah.
And the domain of fx is a whole real number set. The range of the base function is from 0 to positive infinity. 0 is inclusive. Domain of gx is the same with fx, but the range has been changed, right?
Yeah.
Okay, very good. Then how about this one? Can you write it by yourself?
The graph of gx can be obtained by...
No, be careful with the question. What does the question ask you? It asks you to write an expression, right?
-3x squared minus 4x minus 1.
Yeah, that's correct. Because you want to make gx equals negative fx to make a reflection in the x-axis, right? Okay, very good. Alright, next one. Like I said, reflecting the y-axis means the new function is f negative x. Okay, let's see an example. How do we obtain the graph of a new function from the base function? I'll give you 1 minute to think about it.
By reflecting across the y-axis?
Yeah, first of all, you need to check the relation between the new function and the base function, right? The new function can be expressed as 2 times negative x squared, then plus 3 times negative x, then minus 4, which is actually f negative x, right?
Yeah.
So if gx equals f negative x, we say the graph of gx can be obtained by reflecting fx in the y-axis. And then domain does not change because the originally domain is already R. So no matter how you flip it, how you reflect it, it's also R. The range is not changed because we only did a reflection in the y-axis, so that does not change its range, right?
Yeah.
Okay, again, the two reflections can also be combined together. For example, how do we obtain the graph of gx from the graph of fx here? How do you make the statement?
reflect it across the x-axis. The graph of gx can be obtained by reflecting across the x-axis and then reflecting across the y-axis.
Yeah, be careful with the wording, okay? Usually we'll use in, not across. Here, the proposition is in. So note that first you need to establish the relation between the new function and the base function. So note here, gx is actually negative f negative x, right? Therefore, the graph of gx can be obtained by reflecting the graph of fx in the x-axis and then the y-axis. Also, we can do them at the same time, or the order does not matter, right?
Yeah.
Okay, let's do another practice. So how about this one? Again,
gx equals negative x to the power of 3 minus 2x squared minus 3. Sorry, plus 2x squared minus 3.
So fx is reflecting the x and y axis, right? Therefore, yeah, you can write that at the same time. Therefore, gx equals, we have a negative sign here and also a negative sign here, right?
Yeah.
And then that'll give you negative f negative x. F negative x gives you negative x to the power of 3 plus 2x squared plus 3, which is positive x cubed minus 2x squared minus 3. You see that? So your solution here is not correct. You see why?
Oh, yeah. Yeah, we see.
Yeah, because you have a negative symbol here and another negative symbol here. Then you need to simplify that expression. Alright?
Yeah.
Okay. Any questions so far?
No.
Alright, let's see. Vertical stretch or compression. So we have covered the first 4 types of transformations. Now let's have a look at vertical stretch. Again, I'll ask you to make a reasonable guess. Suppose we have a base function like this, and after some vertical stretch, the function somewhat becomes like this. So originally the function is fx. After we vertically stretch it, the function becomes gx. Function becomes thinner. Can you make a reasonable guess? What's the connection between gx and fx? Can you express gx in terms of fx?
X is greater or is greater.
Yes. So probably we need to add a stretch factor a in front of fx, right?
Yeah.
And in this particular example, a is a number that is larger than 1, right?
Yeah.
Okay, let's see what the theory tells us here. This is a little complex. Vertical stretches look complex, so be careful with the statement here. The graph of the function gx equals afx. So note that this is a connection between gx and fx. There is an extra a here. If a is greater than 0, then this is a vertical stretch or vertical compression of the graph of fx by a factor of a. If a is greater than 1, the graph is a vertical stretch by a factor of a, which means you stretch this function along the vertical direction. Make it thinner. or if A is between 0 and 1, open interval, the graph is a vertical compression, which means you just press the original base function, make it fatter by a factor of A. Any points on the x-axis are invariant, which means the point on the x-axis does not change, it's their position.
Okay.
I'll show you an example. So let's see. Okay, let's see an example here. Delete. Okay, so let's use this function as an example. Originally we have x squared plus 5, right?
Yeah.
Let's show its value. This is a function x equals x squared plus 5. So if I add some parameter in front of that function, for example, if I let y equals 2 times x squared plus 5, which is actually 2x squared plus 10, right?
Yeah.
So as you can see here, the function becomes thinner than before, right? Okay,
yeah.
let's use another one as an example. So this time let's give it some zeros. So how about x squared minus 4? And then here, if we add a stretch factor 2 in front, we have 2x squared minus 8. So as you can see here, okay, I'm going to use some other colors. Let me change the color. Let's change the color a little bit here. So the base function is the green one, x squared minus 4, right?
Yeah.
If I times the 2 in front of fx, the function becomes 2x squared minus 8. So as you can see here, the function becomes thinner along the vertical direction, right? But any point on the x-axis does not change. It's still at their original position. Can you see that?
Yeah.
So let me give you another example. So if we add, for example, 5 in front of the original function, then this function becomes y equals 5x squared minus 20, right? So as you can see here, this function becomes even thinner. But still, the point on the x-axis does not change, right?
Yeah.
So again, these are called a family of functions who share the same zeros. And as you can see here, if we simply add a stretch factor a in front of that, then the function is actually vertical stretched. So now let's add a fraction to make it as a vertical compression. So for example, if I put 1/2 in front of that, so what will happen? So that's 1/2 x squared, so 1/2 times 4 is actually 2, right? And as you can see here, the red curve becomes fatter than before, right? It looks like there is a vertical compression to the original green curve, right? Again, let's use 1/5 as the stretch factor to the orange function. So that'll give us 1/5 x squared minus 4 over 5. Again, as you can see here, function becomes even fatter, that there is a vertical compression to the original green function, right? Are you clear with that now?
Yeah.
Again, when a is less than 0, that means you have to do a vertical stretch or compression first, followed by a reflection in the x axis, right?
Yeah.
Are you clear?
Yeah.
Okay. All right, let's see an example here. How do you obtain the graph of gx equals 3x squared from the graph of the original function fx equals x squared? Again, you need to establish connection between the new function and the base function, right? So we can write it like this. Note that. So what is the relation between the new function, base function? Gx is actually just the 3 times the original function fx, right?
Yeah.
So basically add a stretch factor 3. So if every x on of the point on fx unchanged, then the y coordinates of every point has been enlarged by 3 times than before, right? That means a vertical stretch, right? Therefore, we say the graph of gx can be obtained by vertically stretching the graph of fx by a factor of 3, right? This is your stretch factor. You get it?
Yeah.
Okay, if you really get it, then let's check your understanding, use some other example. How about this one?
The graph of gx can be obtained by compressing it by -1/3.
Well, remember the stretch or compression factor is always greater than 1. If you have a negative sign here, that means reflection, right?
Oh, sorry, yeah.
Okay, first try to establish connection between gx and fx. So gx is simply -1/3 times fx, right? So there are 2 types of different transformations. How do you write this? Well, we say, therefore, the graph of gx can be obtained by vertically compressed. Well, first of all, you need to specify the direction, and then specify whether it's compressing or stretching. The graph of fx by a factor. Also, you need to give a factor of compressing or stretching. Of 1/3, and then reflecting the graph in the x-axis, right?
Yeah.
Are you clear now?
Yeah.
Okay, let's have a look at the last types of transformations, which is horizontal stretch or compression. So, and this is the most complex one. If the new function gx equals f of ax, k is greater than 0, is horizontal stretch or a horizontal compression of the graph of fx by a factor of 1/k. It's not k, but 1/k. Can you see why? Because in order to keep y unchanged, your x must become 1/k of the original x0. So that factor is 1/k, right? Careful with that. So have a look at this and let me know if you finish, okay? Do you have a cell phone? Can you take a snapshot of this?
Okay.
Or using your computer, because we are running out of time, right? Yeah, I have another lesson after you. And take a snapshot or a screenshot of this and let me know if you finish.
Yeah, done.
How about this one? I'll give you some examples. Take this example. Okay. Next, actually we can also combine all the transformations. So take a snapshot, take a screenshot of this, and I think in the next lesson I'll explain this a little bit. But you can have a look at this by yourself as well in advance, okay?
Okay.
And note that the order does matter. Usually we need to do the transformations represented by A and K first, followed by C and D, okay? And also take a screenshot of this.
Good.
And this. Last question.
Okay.
So we'll finish the remaining part of this topic in our next lesson. Okay?